All right, in this video, we're going to be working linear algebra homework 4.3. And so we're going to be finding some row spaces and column spaces. So we're going to start by finding the row space and column space of each of these 6 matrices that you can see on your problem set. So the first one is 1, 3, and 2, 6. So M is 1, 3, and 2, 6. All right. Now, I can see that both of these columns are, proportional. That the columns are just going to be, the second component is 3 times the first. So I'm going to say that's the column space. This is not something where I need to do the row reduction. Had I augmented M with Y1 and Y2 and done the row reduction, maybe I will actually show you me doing that one time. And you would see that, in order for us to be able to linearly combine these columns and get, a third column back, we're going to need to have y2 minus 3, y1 equaling 0, which is exactly what I was saying. The second component is 3 times the first component. Okay, so I'm going to say the column space of M is going to equal the set of all multiples of 1, 3. So, you could say k and 3k, where k is a real number. I think that'll do. And then for the row space, again, it's 2 rows that are proportional to each other. Okay, it's a row of 1 and 2 and a row of 3 and 6. And so our rows are just going to be, the second component twice the first. For the same reason as the other one, row space of M is going to be the set of all 1 and 2 multiplied by k, so I'm going to call that k and 2k, where k is a real number. And you could write that as a column or as a row. It really doesn't matter. Vector is vector. Had I done the row reduction, it would have looked like that. And I would have said y2 minus 2y1 needs to equal 0, so y2 is equal to 2 of y1, however you want to call it. All right, so this one's very much the same. We've got a singular 2 by 2 matrix, so the row space and the column space is just going to be kind of all multiples of the one column and the one row that we can actually see. All right, so I'm going to say the column space of this matrix is going to be the set of all, maybe I say y1 and y2, for which y2 is equal to 0. You could just call that y1 and 0, though, if you wanted. There's lots of ways we could write this. And then for the row space of M, that row of all zeros is not really adding anything new to the space, so I'm just going to say it's, instead of all multiples of the row 1 and negative 5. So y1 and y2, where y2 is negative 5 of y1. Right, yeah, y2 equals negative 5 of y, but yeah. All right, and let's move on to the next one. All right, now we're moving on to a wide matrix, and so I'm thinking about this one. Okay, 1, negative 1, 0, negative 1, 2, 3 are my rows. Okay, so I can see if I go and do row reduction, I'm going to end up with 2 pivots. Right, if I add the first row down onto the second row, I'd end up with the second row of 0, 1, 3. Okay, and so that would be a second pivot. So I know I've got a pivot in every row, so the column space is going to fill up all of R2. There's not going to be, we're never going to be able to augment with y1 and y2 and get no solution. That's never going to happen. So I'm going to say, starting with column space of M equals all of R2. The row space is going to be a little bit trickier to find, though, right? Because I've got 2 independent rows in R3. I think I'm going to need to do the row reduction for this one. So 1, negative 1, 0, negative 1, 2, and 3. I'm going to augment that with y1, y2, and y3. And just see what happens. So I'm going to add row 1 onto row 2. So 1, negative 1, y1, 0, 1, y1 plus y2, and then 0, 3, y3. Okay, so I can see the pattern. in order for this to not be inconsistent, I'm going to need y3 to be 3 of y1 plus y2, 3 times as big, because the third row is 3 times as big as the middle row. Okay, so I know that I need y3 equals 3 of y1 plus y2. It's going to be the set of all, okay, y1 and y2 can be whatever they want, and y3 is 3y1 and 3y2. Okay, that's what the row is going to look like. I'm not going to write it out as a row because then it would be hard to tell where the entry stopped. But I'm going to say y1 and y2 are real numbers. I realize I totally did not explain my methodology on that last one for finding the row space, but you hopefully saw in the lesson, if we're going to find a row space, we're going to really just be computing the column space of the transpose, because that's what the row space is. All right, so moving on to D, I've got 1, 0, 0, and 0, 0, 1. All right, so the column space of this one is going to be, just think about any combination of these columns. I'm going to, the first component can be whatever I want, so can the third component, but the middle component has to be 0. Okay, so that's the set of all vectors of the form y1, 0, and y3, where y1 and y3 are real numbers. And the row space of M, let's see, I'm seeing 2 pivots. Okay, so I guess a pivot in each column means the row space fills up everything. Yeah, that would mean that. Okay, so I'm just going to say the row space of M is all of R2. Because, if you think about the first row and the third row, you've got access to everything with those two. You don't really even need the middle row. So this next one, okay, let's start with column space. Oh, it's just all multiples of 1, 2, 3. Yeah, because 1, 2, 3, same column 2 times. Okay, so that's going to be set of all multiples of 1, 2, 3. And I could call it k, 2k, and 3k, or I could just call it that times k, where k is just some real number. And then the row space, okay, each row, I've got the same component twice, right? So the second component is equal to the first component. So I would say that the row space of M, all possible combinations of that, is still going to leave me with rows where I have the same number twice. All right, now the last of these, I'm noticing that 2 of the rows are identical. Okay, so it's going to have a very limited row space. That does, because the square matrix means it's going to have kind of limited column space as well, because something we're going to learn about in this class is the number of pivots in the reduced row echelon form of M is going to be the same as the number of pivots in the reduced row echelon form of M transpose. But I'm thinking for the column space, for both of them, I think I'm going to have to do row reduction. I'm not really saying anything unless, no, this is not one that it is though. It's very similar to what I did in part C, but I erased that work. So I tend to think that the row space for the matrix in part C is going to be the same as the matrix in part F, because we just added another row that was basically equivalent to a row that we already had seen in the matrix from part C. Column space will be totally different because there's that extra row. Okay, anyway, I'm done. Enough stalling. 1, -1, -1, 2, 1, 1, 3, 0, 0. Augment that with y1, y2, and y3. All right, now I can already see that y2 and y3 need to be equal. I can just maybe subtract to kill off that bottom row. 0, 0, 0. y3 minus y2. That's going to need to equal 0. But then I'm going to add down and have 0, 3, 3. Oh, well, I guess that's not going to show me anything else new. Because the first two rows are independent. Yeah, okay. It was easier than I thought. So y1, y2. Okay, yeah. So I'm not going to be able to introduce any other all 0 rows. So really, the whole deal with the column space is that. Oh yeah, thinking I wasn't looking at this as columns. I think I was looking at it as rows. Yeah, the second and third components are going to have to be equal, right? -1, -1, 1, 1, 0, 0. Yeah, okay. So that's, I just did not notice that. But if you don't notice what it is, whatever it is you're supposed to notice, the row reduction will tell you. Right, so it's going to be the set of like y1, y2, and y2. And for the row space, I'm sure there's something else equally as obvious, but I'm going to just transpose this matrix and compute that column space. Oh, I guess if I knew there was going to be 2 pivots, I would say that with the rows, no, I'm not seeing it. Okay, I didn't augment, but y1, y2, y3. Okay, guess I wasn't even calling it a matrix over there. So let's subtract 2 of row 1. Okay, so y2 minus 2y1. And then I'm going to subtract 3 of row 1 from row 3, so I get 0, 3, and 3. Okay, so y3 minus 3 of y1. Okay, so I can see that those two things need to be equal, right? It's the same row, so the things on the right-hand side of the vertical bar would need to be equal also. So I'm going to have y2 minus 2 of y1 equaling y3 minus 3 of y1. I should definitely put all the y1s on the same side. So if I had negative 2y1 and I added 3 back, that would be positive 1y1 plus y2 equals y3. Let's see, is there be enough room? All right, the set of all y1, y2, and y1 plus y2. As a row. Ah, sure enough. Yep. If I add the first 2 components in each row together, I do get the third row or component of that row. Did not notice that. All right. Now they want us to construct a matrix with some given properties. Okay, so this first one is like, okay, it's got to have these 2 vectors in the column space and these other 2 vectors in the row space. Now, I'm just thinking about the columns. Now, the easiest way to ensure that these 2 vectors would be in the column space of A would be to make those columns of A. And I can see that my row space needs to be, a subspace of R2, I guess is what I would say. I need to have 2 elements in each row. Oh, I see what I'm supposed to say. All right, that's my hypothesis. But if I think about, is 1, 2, are 1, 2, and 2, 5 both in the row space of A? Yes, totally. I can get 1, 2 by taking 1 of the first row and 2 of the third row. And I can get 2, 5 by taking 2 of the second row and 5 of the third row. It's very possible. Okay, so that's going to fit the specifications. Big. So 2b is asking for column space is all multiples of 1, 1, 3. So K, 3K. All right, and that's the whole column space. So that means that I can really only have one unique column in my matrix. It's going to just have to be different 113. It could be like 113, 226, something like that. And null space is all multiples of 311. Now this is interesting. Null space. I'm going to use a different letter. Okay, so 3, 1, and 1. All right, so, oh, I know what to do. Okay, so the null space is telling me like some sort of like combination of the columns that could give me the zero vector. So I know that I'm going to need to have 3 columns. And if the column space is a subset of, or a subspace of R3, I know this is going to be a 3 by 3 matrix. All right. And I've never worked this problem set before. I kind of found it, added it to the homework. I thought it was really nice. I see where we're going with this. So I'm going to start with 113. Okay, so if I take 3 of this, and then I'm going to add it to, I'm going to do some scratch work off to the side, 339, and then I need to add the same, no, just plus the same number of, yeah, and for ease, I'm going to just be assuming A is 1, like null, so for null space of A, if it's all multiples of 311, I'm just going to use 311 as the combination, plus, all right, plus another thing, that needs to equal the zero vector. Okay, I see what needs to be done. It would be really nice if I could just say like, oh, -3, -3, -9, and then 0, 0, 0. Actually, that's going to work. Strangely enough, I can't tell if I just like lucked into something or if there was actually, something deeper there. I was going to say if I just choose random stuff that's going to add up to -3, -3, and -9, I chose the most obvious stuff, it might not work because, let me just show you what I was thinking. Just the way I would think of one that worked. Okay, if it needs to be, say, -3 to add up to a 0 first component, so I would say, like -5 and 2. And then if this one needed to be -3, I could make it, -33 and +30, and then -9, maybe 0 and -9. But those columns wouldn't work because they would introduce, new vectors into the column space. These columns are not just a multiple of 113. So I am actually going to go back and say, okay, my best answer for this is going to be 113, -3, -3, -9, and then 0, 0, 0. All right, this one might have been a stretch. I had to translate this one into, vocabulary at this point in the course. It says null space has one more free variable than its left null space. Okay, so let's just make this as easy as possible and just say null space of A has the extra variable, has 2 free variables. Oh, yeah, this is going to be possible. I'm just going to make it a 0 matrix. Null space of A has, maybe I'd make it 2 free variables and then make the other one 3 so it didn't look like not a matrix. All right, so I'm going to make the null space have 3 free variables. That would be, okay, so that would mean the null space needs to have at least 3 components. So I think I would need 3 columns. I think I'm going to go with a 3 by 2 matrix of all zeros. Let me think about that. All right, so the null space of A. No, I said I needed 3 columns. And then I gave myself 3 rows. Okay, so let's going to be a 2 by 3 all zero matrix. All right, so the null space of A has 3 free variables. Yeah, because if I'm multiplying this by A, B, or C, A, B, and C can be whatever they want. Okay, and then the null space of A transpose, that's where I think about multiplying on the left by a row, and that would tell me how to linearly combine the rows. Yep, if I've got U and V, I could take any number of the first row and any number of the second row, and I'm going to get a 0 row. And so that's, 2 free variables, U and V. All right, so that's going to be my matrix that fits that criteria. For 2D, null space contains 1, 3, and column space contains 1, 3. Okay. 1 and 3 is in the null space, and 1, 3 is in the column space. All right. Meaning, okay, so I'm going to just think about, if a null vector has 2 components in it, that means A has to have 2 columns. And if 1, 3 is in the column space of A, that means the columns need to be having 2 components in them. So it's going to be a 2 by 2 matrix. And I think the easiest way to guarantee that 1, 3 is in the column space of A is going to be for us to, just go ahead and make that one of the columns. And then, okay, if 1 and 3 is in the null space of A, that means 1, 3, one of the first column plus 3 of the second column has to equal the 0 vector. So it's a null vector. So, you could go and you could sit and do the algebra if you wanted. I'm just going to say, okay, that needs to be -1, so A is -1/3. And B needs to equal -3, so B is going to equal -1. And that's my matrix A. Right. 2E. I am going to be, row space is the same as its column space, but its null space is not the same as its left null space. We said row space is the same as the column space. I was saying, what if we just had the non-singular square matrix? But then the null space and the left null space would be identical. Okay. Row space is the same as its column space. That means that we've got to have a square matrix, right? Because otherwise they would be living in different worlds. Null space is not the same as the left null space. Oh, I don't think that should be terribly difficult. I don't know why I'm tripped up on this. I'm going to just write down a hypothesis. All right, so I'm thinking I'm going to make the row space, if it's going to be limited, right, then we would need I'm just going to have a limited row space, and maybe it's just 1, 2. And then the column space is the same. Wouldn't that mean that I'd have to have 2, 4 here? I feel like this might not be possible. Yeah, I was not thinking about that the right way. This is not possible at all. And I can actually prove this for you. I'm thinking about it. I'm going to have to retract that. I actually can't prove that for you right now with what we have currently in our class. I think I could show you that the null space of this matrix and the left null space are going to have the same dimension, or for any of these square matrices have the same row space and column space. I could show you that, pardon me, we don't know about dimension yet. I could show you that they have the same number of free variables in them, but I'm not going to be able to actually show you that they're the same space quite yet. But in the next unit, we'll be able to do that. Right, now for F, I hope that this one works. Row space contains 1, 1, 1, and null space also contains 1, 1, 1. Okay, so 1, 1, 1 just needs to be a row. Okay, let's make that easy on myself. And then, so the null space contains 1, 1, and 1. That's not actually going to be possible. As you can just see right here. I'm going to just put A, B, and C. I think this one's a lot easier to see why this is not possible. This one, we're going to have a really good reason for why this is not possible, like once we study orthogonal spaces. But it's not possible for the same non-zero vector to be in a row space and the null space of the same matrix. As we'll see, it will be absolutely impossible. So, but with this one, if I was going to multiply this by 1, 1, 1 and have it be a null vector, what we were saying is that needs to be, 0 and 0. But that would require that 1 plus 1 plus 1 equals 0, but that's not true, right? So that's why this one's going to be impossible. All right, number 3, V is going to be the span of vector U and vector V, and there we got those. So A is a matrix where the row space of A is space V. Give a matrix that could be A. I'm just going to make those the rows of my matrix. 1, 1, 1, and 2, 1, 0. Don't make it too hard on yourself. Then for B, it says B is a matrix where the null space of B is vector space V. Okay, give a matrix that could be B. Okay, so that means that I need to have 3 columns. And I need to be able to add them together and get a 0 vector. I need to change that to say a non-zero matrix that could be B, because otherwise the third part would not be interesting. All right, so B is going to be, all right, need to have 3 columns, right? Yeah. Okay. So, but then if, wait a second. Okay, so after some investigation myself, I realized that I was still thinking about part C, finding the product AB, because I know this is supposed to be kind of a special thing that would happen here. But I was just feeling like the dimensions weren't lining up quite right. And sure enough, it needs to request the product A times B transpose. Now, maybe, if you're working this homework in the future, maybe I've gotten it changed by now. But, okay, so we're going to need to multiply A times B transpose, but we should be able to find, 3 columns where if I add the 3 together, oh, you know what would be easier? Would be for me to start with 2, 1, 0. So 2 of the first column plus the second column needs to equal 0. I see how I'm going to proceed. All right, so I'm going to just say, maybe I'll also make this one, and you'd have 3 columns. Maybe I'll also make this one a 2 by 3. Just to make it a little more exciting. So 2 of the first column plus the second column needs to equal the 0 vector. So, maybe I'll do 1, 2. So 2, 4 plus this one, -2 and -4, that equals 0. But then also 1, 1, 1 needs to be in the null space. If I add these 3 columns together, I need to get 0. Okay, that definitely works because 2 minus 2, 4 minus 4. Okay, great. All right, now I'm going to multiply A, B transpose and see what happens. Just multiply A times B transpose and see what comes back. So 1, 1, 1, 2, 1, 0 multiplied by 1, -2, 1, and 2, -4, 2. Okay, so the first column -2 of the second column plus the third one. Sure. Sure enough. And then, okay, the same twice 0. Yeah, it's going to be a 2 by 2 all 0 matrix. And I'm going to be honest, I don't see the mechanism by which this is happening, but I do think it has to do with, really what we're going to be investigating really the rest of the way through the semester is the relationship between these spaces and how they're all interconnected. So we've done it. We found AB transpose. It was a 0 matrix. That was what I knew was going to happen, but I'm just going to stop there. All right, number 4 has got this 3 by 4 matrix D where it's got an all 0 column and then 2 columns that are identical and then another column that's not too far off. So we want all 4 fundamental subspaces. That's going to be the row space, the column space, the left null space, and the regular null space. So I might just start with column space. I can see that I have actually got... Okay, I'm just going to have my middle component equaling 0. This thing is going to give me freedom in the first component, and if I've got freedom in the first component, I could, I can figure out undo whatever these are contributing, and then really have freedom in the third component. So column space of D is going to be the set of all vectors A, 0, and B. Shorthand. So the row space of D is going to be the set of all vectors or all rows. Let's see. I am going to have the first or the second and fourth components are going to have to be equal. The first component is going to have to be 0. Okay, so 0A, possibly BA, I think, where A and B are real numbers. Think about that. Yeah. Okay, yeah, totally. Okay. And then, we're going to need to probably do some work to find that null space. So I'm going to switch up my color and say, all right, if I row reduce D, whoops. I'll get 0, 1, 0, 1, 0, 0, 1, 0, 0, 0, 0, 0. Okay. And so that's going to be the reduced echelon form of D. Then I'm going to say, all right, well, that just means that x2 plus x4 needs to equal 0. I'm going to have to actually... And then x3 equals 0. So x4 and x1 can be whatever they want. Okay, so the first component's free. The second component is the negative of the fourth component. So the fourth component's going to be B. That's negative B, and that would be 0. Okay, then for the last one, and then for the left null space, I'm going to row reduce the transpose. So 0, 3, 3, 3, 0, 0, 0, 0, and 0, 1, 0, 1. Okay, so let's see. Oh, I'm going to take this thing right there and clear out the remainder of that column, and then I'm just going to have my 2 non-zero rows are going to be 1, 0, 0, and 0, 0, 1. All right, so I can say, all right. All right, so that means x1 needs to equal 0 and x3 needs to equal 0. x2 can be whatever it wants. And, oh, yeah, that does make sense, because if I'm thinking about how can I combine the rows to make the zero vector, and that's what the left null space is, like the set of all ways I can linearly combine the rows of this matrix to give me a zero row. Yeah. Null space of D transpose is going to be vectors of the form 0, A, 0, where A is some real number. Okay, that was a good one. All right. Number 5 says F is a 3x3 non-singular matrix, and we want to find the 4 fundamental subspaces of F. That would be really easy. Okay, the row space and the column space are both going to be all of R3, because F is row equivalent to the identity matrix, or however you want to say it. Okay, and then the null space of F and the null space of F transpose, those are both going to be the set that only has the zero vector in it. Not a very interesting null space. But that's really what it means to be non-singular in the first place. It's the only way you can linearly combine the columns to get the zero vector is by taking 0 of each. So there's not only one vector in our null space. So if M is F and then F again, it's like it's a 3x6 matrix, find the 4 fundamental subspaces of M. Okay, yeah. So what I know what's going to happen with the reduced row echelon form of M. Think about it. Oh, yeah, it's just going to be I augmented with I. So that was part A. I'm probably going to move this. That's going to be I augmented with I again. And I know this because if I take F and I do whatever set of steps to row reduce it, and then I do those steps with it copied again on the right side, I'm just going to have the exact same result. Basically, you're just doing the same row reduction twice. So M is kind of like F augmented with F. You could think of it like that. Okay, so because F was non-singular, it reduced to the identity matrix, and so I'm just going to do the exact same set of steps. And it'll bring the right-hand side also down to the identity. And so that does mean that the column space is going to be unchanged, right? I just added more of the same columns, so the column space of M is definitely going to be all of R3. Okay, the row space is going to be a little bit different. Oh, yeah, that's going to be tough for me to write down. I'm going to write down that the row space of M is actually the span of... I'm going to write down a set R because I don't know where else I'm going to put this. All right, so R is going to be a set of vectors, and I might even write these as transpose, but okay, so that's my first one. The second one probably look like that. Oh, and I said I was going to write those as transposes. And then 0, 0, 1, 0, 0, 1, because these are the rows of the reduced row echelon form of M. Now, yeah, but I don't really know how else to say it besides it's the span of those. Or actually, so really it's just like, I could say the first one it would just be like ABC, ABC. Yeah, I actually kind of like that. I'm going to put that in. So it's the span of R for sure, but let me say it's the rows are of the form A, B, C, A, B, C. Okay, now the null space of M, probably have to be a little bit more careful with that, but the null space of the transpose is definitely going to still be the zero vector only because I didn't add any new rows. So the left null space is still equal to just the zero vector. I feel like I'm really not thinking about this one quite right. I feel like this one should be pretty obvious. So if the null space... Oh, yeah, I just need to... what I should have done, I think, is written out that reduced row echelon form of M. So I'm just going to get rid of all of that after all that effort I spent writing that out. Okay, so... All right. So if I'm thinking about, writing... But yeah, I want the null space of M. Really what I would have done is augmented this with 0 and reduced. Okay, so that would be the reduced row echelon form. And so that would be just saying x1 plus x4 needs to equal 0. So those are the negatives of each other. And then x2 and x5 need to be the negatives of each other, and x3 and x6 need to be the negatives of each other. So I do think that means that the null space of M... Okay. Oh, yeah, okay, I do see how this is going to work. So it would just be like ABC, negative A, negative B, negative C. And you know what? I think I might be wiser to call that UVW, negative U, negative V, negative W. Yeah, I like that a little better. What we're going to learn in the future is that, if you dot any of the rows from M with any of the null vectors or any vector in the row space against any vector in the null space, you are going to get 0. And that would be AU minus AU, BV minus BV, CW minus CW. Yeah, there we go. I like that. Okay, so that's all I've got to say for this one. And we got one more problem. Find the fourth fundamental subspaces of G and G plus the identity matrix. I'll be honest, I do not know what's going to happen when we add the identity. So... Okay, so that's G. Okay, the column space is going to be, I can't have anything but 0 in my third component. So I might say column space of G is all A, B, and 0. Now the row space of G, I'm going to have a 0 first component in my row, so 0, A, and B. Then I'm going to kind of get into the null spaces. Okay, for the null space of G, it's just like if I take 0 of the first column and then any number of the second and third columns, I'm good to go. So that's going to be any vector of the form, no, I said that wrong. I need to take any number of the first column. That's going to give me 0, and then none of the second and the third. So that would be like A, 0, and 0. The left null space, how I would create a 0 row is by taking any number of the third row. So the null space of G transpose is going to be 0 of the first row, 0 of the second row, any number of the third row. And then, okay, that was our 4 fundamental subspaces. 6, part B. We need to write in G plus the identity matrix. 1, 1, 0, 0, 1, 1, 0, 0, 1. Is this one non-singular? I think it is. That was not very exciting because we already talked about what should happen with a non-singular 3x3. Okay. Yeah, I'm seeing 3 pivots. It's a triangular matrix, so okay. All right. Okay, didn't give it a name. Column space of G plus I is all of R3. Let me know if I'm missing something here. Okay, because I don't see what it would be. All right, so that's going to be all for this one. This is a really solid problem set. I'm surprised that, just one page of problems kept me busy this long. But that's going to be all for this video. Thanks for watching.